the insertion sort algorithm. A good way to understand insertion sort is to think of playing a card game. So imagine each item in this array represents a card. The dealer gives you one item or one card at a time. Every time you get a card, you insert it in the right position. First you get 8, you keep it. Then you get 2, you insert it before 8. Next you get 4, you insert it between 8 and 2. Then you get 1, you insert it before all the items. Finally you get 3 and insert it after 2. So every time you get an item, you insert it in the correct position. That's why we call this algorithm insertion sort. Now let's see this in action. So we get 8 and should find its correct position amongst the items or cards we have taken so far. 8 is the only item we have seen, so we assume it's in the correct position. Next we read 2. We should insert it before 8, but how? Unlike the previous algorithms, we're not going to do a swap here. Instead, we're going to look at all the items we have seen so far. If they're greater than 2, we should shift them to the right to open space to insert 2. This is a key distinction between insertion sort and other algorithms we have talked about. Instead of swapping items, we shift them to the right. You'll see why in a second. So 8 is greater than 2, and we should shift it to the right to open space for 2. To do this, first we store 2 in a separate variable called current. Next, we shift 8 to the right. Well, more accurately, we copy it to the right. So it overwrites 2. That's why we had to store 2 in a separate variable so we don't lose it. Now, technically we have stored 8 in 2 places in this array, but conceptually, we can assume that we shifted 8 to the right, so now the item at index 0 is empty. So we store the value of the current variable here, okay? So we inserted 2 in the correct position amongst the items we have seen so far. This is the sorted part of the array. In every step, we picked one item from the unsorted part and insert it at the correct position in the sorted part. So next we read 4. Now we look at the items we have seen so far. If they're greater than 4, we shift them to the right to open space to insert 4. So here we shift 8 to the right. Now what about 2? Should we shift it to the right? No, because 2 is smaller than 4 and it should stay where it is. So we have found the right place to insert 4. All the items we have seen so far are in the correct position. So next we read 1. Again, we should shift all the greater items to the right to open space for 1. Here we should shift 8, 4, and 2 to the right because they're all greater than 1. Now we insert 1 in the correct position. We're almost done. One more time. We read 3 and shift all the larger items that we have seen to the right. Now we insert 3 at the correct position, and we can see our array is fully sorted. So this is insertion sort.
Quicksort. Like merge sort, quicksort is a recursive algorithm. However, when you think of quicksort, I want you to think of the word pivot. A pivot is simply one of the items in the array that meets the following 3 conditions after we sorted it. First, the pivot is in its correct position in the final sorted array. This means that all items to the left are smaller, and all items to the right are larger. Let's look at an example. We're asked to sort the following array. Let's choose a pivot. I'll explain the best way to do this later, but for now, let's just choose 3. First, we move the pivot to the end of the array to get it out of our way. Next, we're going to look for 2 items. Item from left, which is the first item, starting from the left, that is larger than our pivot. Second, item from right, which is the first item, starting from the right, that is smaller than our pivot. Starting at 2, we can see that 6 is item from left. Now starting at the right, we see that 1 is item from right. Let's swap item from left with item from right. We repeat the process. This time, 5 is item from left, and 0 is item from right. Again, we swap the 2. One more time. This time we see that item from left has a greater index than item from right, so we know we're done. We swap item from left with our pivot. Our pivot is now in its correct spot. To prove it, let's review our 3 conditions. As you can see, all items to the left are smaller, and all items to the right are larger. Heap sort. Let's start with some terminology. A heap is simply an ordered binary tree. Get started. We have the following array that we're tasked to sort. In a nutshell, we'll continuously create max heaps to find the largest item. We'll then remove that item from the heap and into a sorted partition. We'll begin by representing our array as a tree. To see how we did that, simply look at the array from left to right and the tree from top to bottom. Now that we have a tree, let's create our first heap. We assume this is an unsorted array, so we call build max heap. Now that we have our max heap, we know the largest item, 9. We swap 9 with the item at the end of the array, 1. Finally, we remove 9 from the tree and consider it sorted. Looks good so far, except we're back to having a tree and not a heap. This time we call heapify, since only the item 1 is out of place. 1 floats down to the bottom, and the largest number heads to the top. We're back to having a max heap. Let's swap the largest number 8 with the item at the end of the unsorted part of the array, 2. We remove 8 and consider it sorted. Again, we need our heap back, so let's call heapify. I think you see the pattern. I'll let you watch the rest of the video without voiceover. We're all done. Our array is fully sorted. Merge sort. A few quick points, then we'll get to the example. Merge sort is usually done recursively. When you think of merge sort, as with other recursive algorithms, I want you to think of divide and conquer. We're going to break our problem into smaller problems in order to solve it. We're ready to sort. We'll examine the individual items, compare their values, and merge them into temporary arrays. The temporary arrays are sorted, but there's work left to do. Let's jump up the recursion stack and continue. We merge our smaller arrays into a larger one, inserting items in the correct order. One more merge, and we'll have our sorted array. And that's it. Our array is now sorted.
Jingle bell, jingle all the way. Over fun to reach right on just stop and say, okay? Merry Christmas and Happy New Year to you all in the house. I hope God will bless your family, your relatives, your neighbors, your loved ones, and I wish you all the best or everything over these years. God bless your Happy Christmas with your Merry New Year. Bye. I'm sorry, it's McCain Gang. Goodbye.